I hope so.
Yes.
All right, let me just get my screen sharing set up here, and you can see my slides.
Your talk looks great. Yes.
Okay, cool. Yeah, so thank you very much for the chance to come and talk about sort of what we see in the corona with SDO and beyond. And I want to really focus on what I think is a special feature of SDO, which is that it does everything all the time really well. It gives us temporal and spatial and temperature coverage, which provides a really excellent foundation to ask bigger questions than just the sort of surface questions, and to bring in complementary data and sort of look at the corona through the lens of what SDO does in different ways. And when they asked me to give this talk, they said, well, talk about beyond the SDO corona. And I kind of wondered, what do we mean by beyond? Is that just going out into the middle corona, the outer corona? And at the time I was reading Charlie and the Chocolate Factory with my daughter, and I got to the part about Willy Wonka's Great Glass Elevator. And I started thinking about how you can have this elevator that goes, not just up and down, but sideways and long ways and slant ways. And I thought that's kind of the approach I want to take to beyond. I want to go beyond in a lot of different ways, up and down and left and right and forward and backward, even in time, and think about what SDO is showing us that's not just at the surface, but deep inside the data. And so I'm going to give you sort of 5 quick examples of ways that I think we have been able to do this with SDO. And then I'm going to give just a few thoughts about the sort of future of what comes next. So let's start with Comet Lovejoy, which, as you probably remembered, was a comet that in 2011 went through a perihelion very, very close to the sun, so close that we actually were able to image it in AIA. And for me, this was a real awakening of sort of thinking deeply about the data that we get from SDO. We looked at the comet, and what we've done in this image is basically to take the maximum brightness in each pixel in this off-point sequence by SDO and subtract out the steady baseline and put that in the blue channel so you can sort of see the comet's persistent path. And then in the red channel, hopefully you can see the comet actually moving along and sort of see how things are evolving in time. And what really fascinated me is, first of all, we could see the comet at all, because who knew you would be able to see a comet in EUV? And a lot of work has been done to sort of characterize why this happened and which ions we viewed and sort of what the processes there were. But also, there were some really surprising dynamics. And you can see this sort of weird kink in the comet's path, where the sort of outflow from the comet's tail suddenly shifts direction all of a sudden. And instead of heading towards the sun, or at least in the projection we have, it appears to be towards the sun, it's headed away. And I don't want to infer too much about what could have caused that, because there's lots of things we can't see. Maybe there's outflow jets and the comet's rotating and it sort of shifted direction. But right here, something changed in the behavior of the outflow as it crossed a certain boundary in the corona. And it got me thinking at the time about how there are these magnetic field lines in the corona that are very close together, but there's potentially very different behaviors right next to one another. And the data doesn't make this entirely clear when you just look at the loops and you say, oh, well, there's loops. You have to dig a little deeper. You need this comet to fly through and probe what's happening in the corona in a unique way to reveal a deeper truth. And so that's sort of my starting point for this talk, that there are things in the data that surprise us and that can change our thinking, but we have to look a little deeper. And I think the deeper we do look, the more surprises we're actually going to uncover. Which brings me to another way of looking deeply, which is to zoom really far in. And let's talk about the high resolution corona. So Sabrina is going to talk about this a little later. I'm not going to go into too much detail on this particular topic, but of course we had high C fly during the SDO era. And we knew from these great AIA images that there's tons of sort of fine features and high-speed dynamics. But if you really zoom in, you can see that AIA is not giving us maybe everything we want. You can't tell, what are the finest scales that actually appear in the corona. And when you bring new tools to the problem and you go in even farther, you see, yeah, there really is something there even beyond the amazing data that we got from AIA. More recently, we have Solar Orbiter, which has an extreme ultraviolet imager that observes in very high resolution. And these are sort of preliminary observations from February of this year, when they were sort of in the checkout period for the high resolution imager. And this these images show dynamics that are happening, if you look carefully, on the course of just minutes. So all these little dynamic events that you're seeing here are happening really in seconds. And the scales we're looking at are a couple of 100 kilometers per pixel, if I did my math right. So we're really uncovering now the sort of corona at the, I think, very close to the finest scales that we're ever going to be able to observe. And we're seeing that there are important dynamic processes that are happening that are even inaccessible with SDO. And I think that's a really revealing and important thing to think about, that when you really zoom in, there's important things that you must zoom in to see, right? These small scale, high-speed dynamic processes are contributing meaningfully to the big picture, to the evolution of the corona on global scales. They're sort of setting the stage for the bigger processes that we observe all the time. And I'll sort of leave it to Sabrina to talk a little more about that. But I think that's another really exciting thing. SDO provided this foundation where we could then say, let's go deeper. Another way that we can approach this problem is with image processing. We can do the old zoom and enhance. And I think these tools that have grown up at the same time as we've had SDO data are really, really cool and important, and have highlighted how there's stuff in the data that's not there at the superficial level. This is a processed movie I got from Nadia Alzate of an eruption last November, observed by AIA in the 171 passband. And if you just watch the movie sort of in a superficial way, yeah, you can see there's an eruption and you can see that there's some post-flare loops in here. But if you process it so you can see everything clearly, you can actually see that there's a particular loop that triggers this eruption. And then everything else follows. And you can see how there's all this fine structure sort of surrounding this eruption that's disturbed when the eruption goes off. If you watch particularly, you can see it up here. And you can see how there are outflows along these fine magnetic field lines that are almost invisible in the unprocessed data. So you can really see how there's a whole bunch of processes that are not easy to see, but when we bring these powerful tools to bear, we develop deeper understanding. And I think these tools have really, and you're going to see these, I think, throughout this session, these processed movies, these tools have really opened our eyes to what's in the data that's not just at the sort of surface level, and helped us develop really important understanding about processes in the corona. Likewise, SDO produced this huge volume of data. I mean, we have an image every 12 seconds across many channels going back for a whole solar cycle. I think it's also highlighted the need for tools like machine learning tools. This is not an SDO image. This is actually a machine learning tool we use on the solar ultraviolet imager on GOES for sort of space weather forecast feature tracking. But nonetheless, it's an example of the kind of feature identification that can help us mine the data in deeper ways. There's so much data. There's no way a human can go through this anymore and understand big trends and identify features in every image. It's just not practical. But these new machine learning techniques, which I think Michael's going to talk about later in the session, are a really powerful tool for us to exploit the data at the sort of global data set level and understand everything about what's in our data. And I think that's another sort of transition that happened during the SDO era as our computational tools have evolved, that's really paradigm shifting. So I just want to sort of make the case that there's a lot more in these data than even it seems. And I think as we go back and mine these data with advanced tools, we're going to find more and more and more really important and interesting stuff. We got to bring the right tools to the job. So we've talked about tools, we've talked about zooming in, we've talked about different ways to zoom in the data. Let's zoom out a little bit and look at what happens when we look at big events on the sun on global scales. So I want to talk about just a couple of eruptions and flares very briefly. The first one in February 2014. This is an X flare, and this is a highly processed movie showing hot plasma in the wake of this eruption that I worked on with a summer student, Allison Bartz, a few years ago. And I think this is something that SDO did really, really well. It sees everything. It sees the hot stuff and the cool stuff, and it helps us complete a picture that we knew was there of the important processes in flares and eruptions, but really couldn't see very well. And when you bring SDO's ability to see plasma at many temperatures together with image processing techniques that allow us to see, for instance, the formation of a structure that's apparently associated with a current sheet, and then the sort of turbulent inflows and heating that surround this region and the shrinking loops that eventually give rise to the flare arcade, all that stuff together, we've really improved our models. We've validated our basic understanding, and now are headed to deep understanding of what are the processes that drive flares and eruptions. But when we looked at flares like this, one of the sort of frustrations that I had is that you see this structure that's apparently a current sheet or associated with a current sheet. You can see the eruption going out in LASCO, but there's a lot of really important dynamics that are happening in this gap region. And I think this is one of the things that SDO highlighted, that there is more to see even when you see almost everything. Well, there are some tools that allow us to explore that region a little more. And one of them we used to analyze an eruption in 2014 in October, and that's the Proba2 SWAP imager. And the reason we used SWAP specifically for this is it has a slightly larger field of view than AIA did. And this particular unique eruption produced post-eruptive loops that actually extended so far out they left the AIA field of view. And so if you really want to understand how they formed and how they grew and how long they persisted, you have to leave that field of view and take in a bigger picture. And that's what we did with Matt West and I. And it turns out that actually, conveniently, the GOES soft X-ray imager happened to also see this eruption in an orientation that allowed us to look at the growth of this loop structure, which we see as a void in this particular channel because the material is too cool to be observed, over the course of 2 full days. And you can see that above this big, giant growing loop arcade is this sort of persistent, diffuse bright stuff, which indicates that there's a lot of heating going on, and probably that reconnection had persisted for the whole duration of this sort of 2-day growth phase of these giant loops. And that's interesting in its own right, because this is a really unique event. We don't see events that produce loops this big very often, and we don't see events that last this long very often. But it's also interesting because of what happened after this eruption. So this same active region went on to produce something like 3 dozen big flares and almost no significant CMEs in this as it sort of rotated across the disk. And there's been some good work on sort of how we got there. But I think what fundamentally happened is this first eruptive event that produced this giant post-flare arcade extracted a lot of free energy out of the sort of higher parts of the corona, so that when this very complicated and highly sheared active region was producing flares, there wasn't really anywhere for that ejecta that might normally erupt to go. They just ran into a wall of potential magnetic field. And you end up with these really strong but confined events that are really unique and important for our understanding of the processes that can cause flares and trigger flares and drive eruptions, but also for space weather forecasting and a whole bunch of things. And this is something that we wouldn't have without SDO, without this full-time monitoring and then the complementary observations that allowed us to fully understand what happened in this event. Finally, I want to go to September 2017. We saw the sort of biggest flares of the whole last solar cycle. And this is a SUVI observation, and you'll see why we're going to use SUVI. Because of its big field of view, or its slightly larger field of view anyway, we can see how this particular eruption on September 10th triggered a sort of global shock that bounced around across the whole corona. You can see the eruption go out here, and then you can see this shock sort of propagate around and bounce off the coronal holes. How this one event really disturbed the whole corona. And there's some nice, tons of nice work on this event, but one nice piece is by Astrid Verenig, who was able to track the growth of this eruption and show that it really expanded laterally very strongly early on. This is facilitated by SUVI's field of view. SDO doesn't actually go out far enough to track the full growth of this eruption. And that's what triggered this shock. And this shock turns out to be really important because this event generated a very strong SEP event that was felt basically everywhere in the heliosphere. And if you think about how SEPs travel and how they're connected to field lines, you need a big global shock to send SEPs streaming out in all directions, to the backside of the sun, to the front side of the sun. It was detected at Mars, it was detected at Earth. And this is where sort of bringing in now a bigger global picture really helped us to develop deep understanding. This eruption also gave rise to another one of these current sheet structures, which we saw with SUVI. And there's been a whole bunch of nice work analyzing just the dynamics here, that the properties of this eruption and how it connects to reconnection. Dana Longcope has a really nice paper using AIA data where they made height time diagrams along this structure and tracked a whole bunch of inflows, and were able to infer the reconnection rate, validate and invalidate some potential models of reconnection, and show that the reconnection that happened in this event was pretty patchy and bursty and not just sort of the steady Sweet Parker pet check paradigm that people looked at for a long time. With SUVI, with a student, Chris Totzauer, we were able to look at this event and how it sort of unfolds, not just down here low in the corona, but with some image processing, see how it gave rise to things that are farther out, and see inflow-outflow pairs. And Chris constructed another one of these high time diagrams where you can see a bunch of strong sort of outflow signatures early on, and then these sort of echelon shapes later on that indicate inflow-outflow pairs that are disconnection events, sort of little bursty reconnection that happens later on. And we can connect then these outflows up to sort of little bursts that we saw in LASCO before the SEP event sort of overwhelmed the imaging, in order to connect, the whole thing globally, what's happening in the low corona and what's happening in the outer corona. And I think this was a really special event. It happened in just the right place. It had just the right characteristics to create an environment that was really rich for mining, the physical processes that underpin the eruptive flares. And it happened because we were able to bring a whole bunch of different tools in, right, on this foundation of what SDO gives us to get a global picture. So I think, the point is EUV has been really critical to our understanding of flares and eruptions, but some of these other instrument capabilities and new capabilities we're still developing are gonna help us really extend that understanding a lot farther. Okay, the last thing I want to highlight is the middle corona. People who know me know that I love to talk about the middle corona, so I couldn't give this talk without getting to that. And AIA has played an important role in helping us learn a lot about the middle corona. So, back when AIA was flying, I was working on Proba 2, and Proba 2 had pretty limited capabilities. It's a very small imager. It only had one channel, 174. But it did have this large field of view, and we found if we stack a bunch of images, we were able to make these beautiful movies showing sort of structures evolving in the corona beyond what we see with SDO on large scales and on long time scales. But it really left us wanting more, right? Because you can see that these things must connect to something that's further out. There's clearly something to be seen, but even this larger field of view out to 1.7, 1.8 solar radii doesn't get us quite all the way there. So what was there? Well, AIA actually provided a great opportunity to explore this, because it turns out AIA does regular off points for its flat field. And by taking a bunch of these off points that were intended for flat field generation and stitching them together, we were able to start tracing structures out to 2 solar radii and even to 3 solar radii, and show that the EUV corona extends far beyond what we originally might have expected, really out like far into the sort of middle corona to places where we normally observe in white light. And we were able to do this with Proba 2 a little later with some Proba 2 off points, showing the same region sort of as it rotated to the other side of the sun. These very large fan-like structures had persisted and were again visible out to 3 solar radii. And this set the stage for what I think is sort of the new frontier now that we're getting into with large field of view EUV imaging in general. A few years later, we were able to actually run a long-term off-point campaign with SUVI, where we were able to sort of make these 3 panel mosaics that really show the dynamics of the corona in EUV on large scales. So now establishing that deep connection from the low corona all the way out to what we see with LASCO. And in this movie, which actually combines 2 channels, 195, which is blue, and 171, which is gold, we see a whole bunch of really surprising and interesting things that I certainly didn't know was there. And I will point out it's noisy and it's full of stray light. SUVI was not meant to operate in this way. But nonetheless, you can see really interesting eruptions over here. Here's one right now. You can see all sorts of little jets at the poles, and even from these sort of little rays in 171 that don't form at the poles. Over here, if you watch carefully, you can see there's a bunch of sort of gradual disconnection events and more bursty things. You can see this very turbulent, complex evolution of coronal structures on the long term. And I think, without AIA to sort of open our eyes to explore the idea that there was something out there, we wouldn't be making observations like this. We wouldn't be thinking about new instruments that can do this routinely. If you combine the SUVI observations with LASCO, you can actually see that the stuff we're seeing in SUVI, and this is the 195 channel superposed on LASCO C2, each one of these little outflows, each one of these little bursts that we're seeing in the EUV connects to something that's visible in the coronagraphs. And so for the first time from the Earth perspective, really since the beginning of the SOHO mission when we still had C1, we have this fully connected view again where we can link the low corona all the way out into the, the outer corona and see this highly connected environment, this highly complex evolution of the structures in the magnetic field, and reveal a whole bunch of phenomena that I certainly had no idea were there. And I think that's really exciting. There's an inflow right here, actually. So there are things actually coming from outside in the corona back to influence the inner corona. I think it's really exciting.
5 minutes.
Thanks, Laurel. So, we've done a few more off-point campaigns. Dean mentioned that there's going to be some off-points. I hope we're going to get one for the Parker perihelion that's coming up. This is just another one from 2019. We refined our scheme a little bit. We got rid of a little bit of the sort of noise and stray light, although it's still challenging. But again, you see these really complicated and cool dynamics here. So, going beyond now what we've done with SDO and looking ahead to a future where we can link the kinds of observations we've been making now for a long time to something really new and exciting. So, I think this is my last sort of big lesson. UV images of the middle corona are going to unlock major mysteries. And so let's talk for just a couple of minutes at the end here about the future, okay? So I'm going to give you just a few recommendations. First, I want to encourage everybody to think long-term. What is the future of coronal observations going to look like? I don't know the answer, but one thing I can tell you is that we have a whole fleet of solar ultraviolet imagers on the GOES spacecraft. They're going to live out to 2040. And so this can be another foundation that bridges us to the next set of big solar missions, a long, consistent baseline of self-similar observations. I think this, we have to exploit this and use it as the sort of link to the future. And I hope we're going to have AIA for a good long time too there, but even out to 2040, we should have these great observations from SUVI. And I think we need to think about, how do then we take all of the disparate observations we've been making for the past 25, 26 years, going back to SOHO up to now, and then linking into the future of the corona across many EUV wavelengths and make them interoperable. And I want to challenge people to think about, how can we build long-term calibrated interoperable data sets? What tools can we use to mine the data sets we already have more deeply on the long term? Because I think there's more there even than we've been able to exploit so far. Second thing, I want to encourage people to think big. I showed you the SUVI off points. These are those were from an imager that was not meant to do this. Now we have an imager, the full sun imager on Solar Orbiter that is, and these are very preliminary. As you can see, there's a lot of work to do dealing with the noise and how to sort of process the data. But the full sun imager on Solar Orbiter is seeing the same stuff we saw with SUVI, and it's seeing it in its natural field of view. And I think as they get FSI dialed in, you're going to see amazing things. And of course, we're going to get out of the ecliptic too and see a totally new perspective, which I think is just so exciting. There's a whole bunch of mission proposals coming out, Sunset, Cozy. I want to challenge people to think, what new missions can finally close these gaps in our understanding of the corona on the largest scales? Next, I want to encourage people to think coherently. Stereo gave us this view where we can actually track structures from the low corona with careful image processing all the way out to the Earth environment. We need to think of the corona and the heliosphere as a connected global system. What happens down here in the low corona matters up here, but vice versa. What happens up here in the outer corona can actually influence events in the low corona. That's one of the things we're seeing with the SUVI off points. We have to build more missions that can stitch together this sort of global picture of what's happening in the corona. And this is from a white paper we've written for the new Helio 2050. I really want to encourage people to think about, how do we take the resources we have, the resources that are coming online, the resources that are planned for the future, and develop a sort of fully coherent observatory that gives us that complete view of the corona as a single system. Because I think that's the new frontier. I think that's where the big questions, the big unanswered questions still lie. So how do we develop new observatories to provide us with well-coordinated measurements required for the systemic global understanding? Okay, I want to encourage people to think of what we're missing, right? There are other ways to explore the corona that we don't always exploit to the full extent. We can go to eclipses. Eclipses provide a ground where you actually can make these global observations. really, really cool special observations where we see the whole corona all at once. We can exploit at eclipses band passes, wavelength regimes that are hard to access, like the IR. So we have these great observations of the IR corona from 2017 from Amir Caspi's NASA WB-57 mission, where we see all sorts of features we didn't expect to see in the IR. And then we have these great tools that allow us to mine down the data and see faint features, the origins of stealth CMEs, for instance. And if we bring those together, I think that's a really, looking at what are all the novel ways we can sort of piece together additional information, mine the data, that opens up whole new pathways. So what innovative approaches for data collection and analysis can help us resolve the big open questions in coronal physics? And finally, I want to encourage people to think from new perspectives. We've been looking at the corona like this for a long time. And these are great models that Cooper was kind enough to provide for me that show the predictive science renderings of the corona from the 2019 eclipse. Because this is a model, we can take it and turn it on its side and look at what the corona looks like from above. And I think this is really cool. And I hope that Cooper will be able to tell you a little more about this kind of modeling in his talk. But this is a view that we really need. We need to go from this same view we've had for a long time to one that can allow us to understand how the corona connects globally, how the poles are structured and how they drive the dynamics in a totally unique way. And so I really want to ask the question, what missions are we going to develop that are going to leave the near Earth environment, leave the ecliptic, and give us critically needed data that we have no access to yet? There's proposals out there, Solaris, for instance, but I think this is another opportunity we really must be thinking about as we look ahead to the next 30 years of solar observations. And with that, I just say thank you to SDO for all the many years of great observations, and for everybody else who's worked on the missions that have, working together, created this great global, heliospheric system observatory that gives us the whole picture.
All right, well, thank you, Dan. That was an excellent little talk as we ride off into the sunset. Nice selling point for sunset.
Yeah.
I do not see any questions for you in the Slack, or excuse me, in the chat.
Okay.
So
There were a
hopefully,
couple of comments. One from
Yeah, there was one comment about the stereo instrumentation and how they can see seamlessly. There's overlap between the EUV and the white light fields of view on stereo.
Yeah, I think that's a really good point. And I hope I did emphasize that. I think doing that routinely then from multiple perspectives, getting from the Earth view, I think that's going to be really important in the future.
and also Mark Chung has a comment about the AIA point spread function deconvolution, and perhaps we could encourage that in the SUVI images as well.
Yeah, that's actually something we're working on and exploring. It's a little more complicated in SUVI, it turns out, than AIA because just the construction of the instrument. But that's something that Chris Bethke has done a great job already, I think, getting us most of the way there. And we will certainly put out SUVI tools very soon that do that kind of processing for people.
Right.
We have a couple more questions now in the chat. Let's see, we have a question to Dan and Cooper about showing less structure in the middle corona in the models. I'm wondering if maybe we should wait and discuss that question after Cooper's talk.
Yeah, I think the answer I would give would be highly superficial. And so let's pin that one for Cooper, who will be able to answer that adequately.
Phil Chamberlain said that you made a comment that we'll never again have higher spatial resolution like than the solar orbiter, the SOLO imager. Why would you say that?
Yeah, I don't know. I mean, maybe I didn't articulate that quite well enough. We could go deeper, but I think what I mean to say is that I think we're finally getting down to the fundamental scales in the corona that really matter. Now, somebody will probably prove me wrong in 10 years, and I really encourage that and hope that happens. But I think, when we got AIA, it seemed like, wow, we're really finally getting there. And then when we drilled down farther, we see that the corona is this sort of fractal environment. You can just keep going down and down and down. So I hope that, yeah, somebody will prove me wrong and show that, well, it matters if you can get down to the kilometer scale. I think we're getting to some of the current technological limits of what you can build and put in space and, you know, in an affordable way. So this is where we are for now. But I think that's a fair comment that we should still be looking to go deeper, new technologies, things like photon sieves that can, yeah, sort of create paradigm shifts in how we image the sun might actually take us a lot deeper.
Great, thanks. We have to move on to the next talk, but Dan, I encourage you to look at the questions in the chat that we didn't get to.